Hello, everyone. Can you hear me? Hello, I can't see you. I see yes in the chat, but I can't hear you, so I'm not sure whether my speakers are working. So could you please say in voice, can you hear me?
Yeah, we can.
Oh, okay, so much better. Fine. Otherwise, it might be, you're asking a question and I can't even understand. Okay, so first of all, I'm in discussion with the Department of Education to move our exam forward. So it was originally planned for the 20th of December. We realized that it is quite too late and it would be better to have it just after completion of the course. So what we will do, there will be a lecture today and the lab. And the final lecture and the lab are planned for Thursday. Same time. I hope you don't have any conflicting exams or anything at that time. And then next week, can you please indicate what about next week for you? When would be best time for you to have an exam? Maybe same time on Monday next week?
Yeah, I guess during the usual time.
Yes, during the usual lecture time. How about
at 10:40
at 10?
Monday?
Yes. Would it be okay? Great. Great. So let's do that. And then you don't have a gap between our lectures and the exam. I will also post some books on the topics we have discussed, in particular Ethereum, into our Telegram channel. I can't do it in Moodle because these are PDFs downloaded from the internet, but it is perfectly okay to send them to Telegram. Okay, so last time we completed our discussion of Ethereum. As a quick recap, let us see what we have actually learned that time. So what are the fundamental differences? Can you recall what are the fundamental differences between the Ethereum blockchain and the original Bitcoin blockchain? So what is really important as a difference between them?
Smart contracts?
Well, Turing complete smart contracts. Smart contracts
Yeah,
in a
not
very,
redundant.
yes, rudimentary form do exist in Bitcoin, but Turing complete smart contracts, yes. That's number one. If we have smart contracts, Turing complete ones, then it turns out that we can't execute arbitrary smart contracts simply because they may turn out to be far too expensive, right? They could lock up the whole network. Actually, today we'll review Hyperledger, and we'll see that in Hyperledger, this problem is solved in a slightly different way compared to Ethereum. So what does Ethereum do in order to manage potentially unlimited expenses of smart contract execution?
The notion of gas?
Yes, Ethereum introduces gas. You run out of gas, your car is not moving. Okay, now from let's say the consensus protocol. What are the differences between Bitcoin and Ethereum? We would say in the first generation, not much. Both of them are proof of work based consensus. Only this proof of work requires that there is some variable part in your transaction block which you can alter in order to compute new hashes before your hash appears to be under the difficulty threshold, right? So if you can recall, what is the difference in how hashes are computed? In Bitcoin, you alter the nonce, timestamp, and extended nonce fields, and that's it. In Ethereum, there is a special directed acyclic graph, DEG, which is prepared for you by the node, and you take subgraphs of this graph, encode them, include them into the current block, and compute the hash. So there is a higher variability of those subgraphs compared to the fields alterable in Bitcoin, which you can use in order to compute your hashes. So basically your hashing space is larger. And in the second generation of Ethereum, which was promised many years ago but still not live, you would have proof of stake compared to proof of work consensus. As you can understand, economically, proof of stake only means, well, is only possible if the asset which is at stake has any value. Okay? If I implement complete, I'm very sorry, but it is a standard term in blockchain technology, which is called shitcoin, then it is probably a little bit early to implement proof of stake based on that, because anyone can discard those coins without any regret. All right, so there's not much is at stake in that case. But if it really has some economic value, and eventually it is convertible into fiat currencies, then proof of stake can, of course, eventually be implemented, and it will probably be implemented in Ethereum. Okay. So apart from that, I wouldn't say there are any fundamental differences. Well, there are some technical differences regarding the hashing functions, hash sizes, things like that. Yes, of course. But this is definitely not of fundamental importance. But now, today, we are going to discuss completely different story. We're going to discuss enterprise level blockchain technologies, and all the enterprise level, some kind of enterprise level applications are possible on top of Ethereum. But nowadays, this is normally not the case, and they are implemented using another stack, which is Hyperledger. Let me put it that way. In Ethereum, your typical applications which you implement are still financial technology applications. So typically, if you have the Ethereum network, Ethereum blockchain, then you implement a certain new coin or new token on top of Ethereum. That by far is the most common application area for Ethereum. So what does it mean? What is a coin? A coin is a smart contract, nothing else. What does this smart contract do? It basically supports only one operation, very much like for Ethereum itself. But for Ethereum itself, it is embedded into the semantics of the virtual machine. So the virtual machine itself knows about Ethereum, at least because it knows about how to convert gas to Ethereum, how to subtract Ethereum, how to subtract your transaction fees. So it knows about Ethereum as a currency. But in smart contracts, you can implement any other tokens which stand for some economic assets. For example, it could be any other currency, it could be an interest rates contract, it could be a private equity on which I should probably stop for a few minutes and tell actually more about that. You implement a smart contract, and the only operation of this smart contract would actually be transaction. Take it from account A and add it to account B. Very much like what we have already seen in the smart contract example. You remember when we considered Ethereum. Only that one was moving the value in Ethereum. This one would be moving the value in this new contract, all right? In this new token. And because of this, okay, moving the value. So where is this? Where is the current value stored in that case? So you see, there is a notion of accounts in Ethereum. And by the way, that's yet another difference which we didn't mention, that in Ethereum there are accounts with the current value. In Bitcoin, there is only a notional view of accounts or wallets. So basically, your current value of a wallet in Bitcoin is just all unspent transaction outputs which you can get hold of. How can you get hold of them? By, first of all, if you're in a possession of a private key and the corresponding public key was mentioned at the destination of that transaction, or if, for example, it is a general, very rare, but general transaction to an arbitrary destination, something like that. Whereas in Ethereum, yes, there is an account and there is a current value of the account, not unspent transaction outputs, but the accounts. And then there is a nonce field which prevents double spending of transactions in the sense that all transactions are numbered through. So basically this nonce to some extent stands for unspent transaction output. Only in that case there is a unique transaction ID, cryptographically unique in Bitcoin. In Ethereum, we have a sequence number of transactions. But the value which is associated with your account is only the value in Ethereum. So when you send a value, if you remember there are such transactions, to an account or to a smart contract, it is the Ethereum value, not any other coin. So if you need to implement yet another coin which is owned by parties in your Ethereum network, then you make use of this persistent storage. If you remember, persistent storage associated with smart contracts. This persistent storage lives in the blockchain as well. And your smart contract updates this persistent and distributed storage, which could be, for example, a key value association. So the key is the account ID, and the value is the value in that new coin rather than in Ethereum. And smart contracts specifying certain coins or assets or the general term now is indeed digital assets, became so popular in Ethereum that the API of those contracts had even been standardized. And the standard is called ERC20. There are next generations now, but it is still the most widespread one. ERC20 is just an API standard of how smart contracts transacting certain assets or coins or digital assets should be designed on top of Ethereum network. The operations are very simple. It is just a transaction. You may build more complex stuff on top of Ethereum. For example, again, typically belonging to the fintech area. Have you heard anything about? Let me actually discuss this in brief. Called DEX, Distributed Exchange Technologies. DEX, for distributed exchange. Any idea what it is and why they are distributed?
Is it something something like DEX in the end of is some variation of letters in word NASDAQ? Something like exchange of equities and commodities, for example.
Generally, yes.
Or internal exchange and measure of accounting inside of
generally, yes.
Inside of some company.
Well, no, it is more like you are right, equity exchange. Let me explain how it works. If you ever exchanged your cryptocurrencies, for example, Bitcoin for Ethereum or Bitcoin for USDT or Tether, which is a crypto dollar or blockchain equivalent of dollar, or exchanging your fiat currency to cryptocurrencies or other way around, then you're using some crypto exchanges. And obviously, there are many reputable, high standard, reliable crypto exchanges nowadays. For example, Binance, BitMEX, OKEX, Huobi. I mentioned them, some regulated European Union and American exchanges like, for example, Bitstamp, Kraken, Gemini, Polonix in the United States, and so on, Coinbase, etc., etc., etc. But there is a fundamental problem with that. In order to exchange your Bitcoins for Ethereum, what you do, you first send this Bitcoin amount to a wallet address, which we know in Bitcoin there is no such a thing as a wallet, but in fact it is a hashed public key, a certain address, which is associated with your account at the exchange. Then it appears on your account and you can trade it using the standard financial trading technologies or order book, orders, and so on. Then it is traded. All is fine, but when you do that, there is a fundamental problem which immediately affects the whole idea of distributed ledger technologies. Once your funds are sent to the exchange, to the wallet, so-called your wallet associated with the exchange, the funds are lost for you, in the sense that it is not your wallet from the distributed ledger point of view. Your wallet is whatever wallet over which you hold private keys, right? Then, and only in that case, it is fully under your control. At the moment when you send your funds to a wallet which is notionally associated with you, but you do not hold private keys for that wallet, then you're at the mercy of the exchange. The exchange may lose the funds if, for example, it is hacked and the funds are stolen, or the exchange may very well misappropriate your funds and disallow you to withdraw them back, which does happen. For example, a very popular European crypto for fiat exchange called DSX. It was officially registered in the UK, but developed by a team of software developers in St. Petersburg. It was quite popular, for example, last year. You could use this, for example, to exchange your cryptocurrencies for euro. It is important that euro, not USD, and then use the European payment system, the official financial European Central Bank established SEPA, single European payment architecture, to get them transferred to your bank account. And at some point, this DSX exchange simply disallowed withdrawals. So the funds sent from this exchange to the clients became frozen, and they're not unfrozen yet. This is a very, I would say, unpleasant, but unfortunately quite typical situation which may occur. When we read about all those vulnerabilities and incidents related to loss of crypto funds, very few of them actually are associated with vulnerabilities of the distributed ledger itself. As I mentioned, there was one very early incident in 2010 with Bitcoin, but nothing really since then. There was a very unpleasant incident related to a hard fork in July of 2016 with Ethereum, and a few smaller scale incidents, but not that many after all. With smart contracts, obviously they appear to be more frequent, much more frequent than with a very simple stack machine of Bitcoin, because yeah, they are Turing complete, and you could get lots of unpleasant effects like unlimited recursion or calling methods across smart contracts, which would eventually result in either some kind of security barriers violation or stack overflow or anything like that, and the whole story would result in undefined behavior. And yet, although this did happen and may probably happen again with even with Ethereum, who knows, or let alone with new blockchains, not that many incidents happened with blockchain technologies themselves. All incidents of stealing funds from distributed exchanges, sorry, not from distributed, that's the point, from centralized exchanges, from normal, conventional crypto exchanges, were related to attackers somehow breaking into the exchange and getting hold of private keys, which are stored by the exchange. Or this could be due to some traitors at the exchange itself, or the exchange like DSX may simply disallow withdrawals and misappropriate the funds submitted to the exchange. The whole point is everything is under your control as long as you and only you hold the private keys. When you submit your funds to the exchange to exchange them, then for that moment and before the funds are withdrawn back to you, it is they, not you, who hold the private keys. And you are completely at the mercy of the exchange and whatever person who could get hold of their keys. Scary, isn't it? And then the idea is, why should we do that? Maybe we can implement the whole exchange as a smart contract And in that case, operations of this exchange, so for example, it would be a smart contract holding your accounts in multiple cryptocurrencies on, say, Ethereum platform, there would be, I would say, relatively sophisticated operations such as order books and matching orders into transactions implemented again as smart contracts. So basically you activate by sending an order, you activate this smart contract and you get a trade against someone who submitted a maximum, so-called limit order, maximum price order previously. What I'm thinking about, and in that case, everything happens in a purely decentralized environment. There is no exchange which can be broken into or which can stop withdrawals. This smart contract, if implemented correctly, it would indeed perform the exchange, perform exchange operations, and then let's say update your account maintained by another smart contract which maintains whatever new coin. So for example, to implement this functionality for Ethereum, you need what? You need both Ethereum and another currency, for example, Bitcoin, on the same Ethereum blockchain. Normally, we know that Bitcoin is on Bitcoin blockchain, which is incompatible with Ethereum. Actually, incrementing after that your Bitcoin account might be possible, but in this case, it is a cross-blockchain call, which breaks these consistency guarantees. What if the gateway between the two blockchains, for example, fail at that point? Whereas if both currencies are implemented in the same blockchain, then you can do it. And if I remember correctly, there exist even Bitcoin implementations on top of Bitcoin-like implementations on top of Ethereum, although obviously this still rely upon some gateway between the official Bitcoin blockchain and the Ethereum blockchain. What I'm thinking about, all of you are welcome into our second stage of blockchain technology, distributed ledger technology course. So the first one was this. The second one will be in the spring term about smart contract programming. So it might be that we'll take it to be project-based rather than lecture-based. All the theory we already know. And we'll implement something quite non-trivial. A very good candidate for our implementation will be indeed a distributed, maybe a coin on the Ethereum platform and a distributed exchange for that coin. I'm absolutely sure it will be interesting, challenging, and will provide you with hands-on experience in Ethereum, if we do it at the Ethereum platform, Ethereum programming. So I think we'll do something like that. So, by the way, while talking about this and smart contract execution, I would like to give you a simple feedback about our midterm. Obviously, midterm was not difficult. There is only one interesting misconception which almost everyone, except probably 2 students, made. There was a tricky question. The smart contracts language in Bitcoin, is it prefix based or postfix based? You remember this question?
Yes.
If we put first 2 operands on the stack, or 1 operand, and then operation, so operands first and operation after that, it is postfix. Post means after. Have you seen the language like PostScript and its more modern version, which is Adobe PDF? PostScript and PDF, say PDF is just compressed PostScript, nothing else. They are programming languages. They are programming languages which allow you to render graphics, including very complex things. No, so you can draw arbitrary lines, shapes, polygons, circles, ellipses, text at any language, and so on. So this is a programming language for rendering graphics, and it is called PostScript precisely because it is very similar to this Bitcoin language, only appeared 30 years prior to that, almost 30 years. Operands first, operation after that. Therefore, it is PostScript. So same for Bitcoin. But if we want to move beyond financial technology alone, and we consider enterprise, general enterprise grade blockchains, then the mechanisms offered by even by the Ethereum network are not at all enough. So let us examine what is required in order to build enterprise grade blockchains, what for, and how the Hyperledger Technologies framework can help you with doing that. I must admit that unlike financial applications, for example, with Bitcoin and Ethereum, I myself, I haven't been using Hyperledger that much in building real life applications. And even to be honest, I'm not completely sure that the Hyperledger approach is ideal. In the chain, I briefly mentioned it in one of the lectures, which is our attempt to develop again an enterprise grade blockchain ready for running mission critical tasks, such that a control system for fueling aircraft for the joint stock company Aeroflot, yes, same big Aeroflot, the Russian national flag carrying air transportation company. We took a completely different approach compared to Hyperledger. It was possible to use Hyperledger to develop this application, yet we decided that to some extent it is too complex, too flexible. Flexibility is not necessarily a good thing. Too sophisticated from the reliability verification point of view, that it was better not to use it and instead develop our own lightweight, well understood, and what is most important, formally verified, as I said, blockchain technology. But Hyperledger does it differently. So in an enterprise blockchain, there are many actors or agents which are not present in this classical Bitcoin and then Ethereum blockchains. Let's look at this graph, for example. For classical networks, yes, we do have a blockchain developer, we have a development community, we have for Ethereum even smart contract developer. But we don't, apart from the core development team, we don't have, for example, a blockchain architect, because what you do, you simply comply to the spec which is already there. It is completely unregulated. I mean, blockchain of Bitcoin or Ethereum, and therefore there is absolutely no regulator role which would perform some kind of oversight of transactions and otherwise fair use of this blockchain. Whereas in an enterprise application, especially in a regulated area such as financial or maybe medicine, maybe some others, regulatory oversight is compulsory. And in that case, regulators must have some machineries to access your network to examine transactions and so on. Blockchain user in the classical blockchains is typically, not always, but typically is a private individual, and that's why they are viewed as just, this democratic money for all. Whereas the blockchain user in an enterprise system is a business user, it is a corporate entity, which typically performs not just person to person, but business to business transactions. And the value of the transactions is typically larger. Other dependability requirements are higher. It needs to be integrated with enterprise accounting system, obviously, because as you can imagine, it is not only part of enterprise own financial management, but it is also part of possibly regulatory and taxation regime. Unlike, and that's very important, the democratic Bitcoin and Ethereum, so that everyone can start and run a node and insert transactions. Enterprise networks are typically private or authenticated networks. An arbitrary outside person is not allowed to access the blockchain and make transactions. It is by membership only. That's why there are membership services here. Typically, you need credentials in order to be able to perform transactions. Credentials are in the form of digital certificates. You know, this X509 public key and certification framework, right? You do, because you are from the computer security track. Yes or no?
Yes.
Okay. What is the membership certificate
Yes.
then? Please explain to me, what is the membership certificate and how it is used to authenticate the user?
As far as I remember, it is a signature used to identify this membership.
Well, simply put,
based on public cryptography.
well, generally yes. In more detail, there is a certain service which is called CA, Certification Authority, all right? And this certification authority, first of all, it would validate your identity. So you really need to come in person to that certification authority. Or if you can't do it in person, then there is a notion of the chain of trust. So basically you come to someone else who knows you, and they are authorized by the central authority to authenticate you on behalf of this central authority. Somehow they really know that you are yourself. In the presence of them, you generate your private key and your public key in the presence of them. They see that the keys are generated, but the certification authority obviously does not receive your private key. The private key is retained by you. What they do, they, having seen that you have just now generated your key pair, and that is your newly generated public key, they certify with their own digital signature that this public key really belongs to you. That Mr. Donald Trump comes to this certification authority and they assure that this public key really belongs to Mr. Donald Trump. And if Mr. Donald Trump requires access to this blockchain, then what they do? They issue a pass, which is precisely called security certificate, which assert the fact that he is authorized to access this blockchain. What does it contain? It contains, again, the newly certified public key of Mr. Trump, and the certificate is signed by the private key of the certification authority. In that case, when this certificate arrives along with the public key of the user into the blockchain is able to perform the verification. Okay, so it is signed by the certification authority. The public key of the certification authority is universally known. That's very important. The wider it is known, is the better. So it is probably in the set of pre-configured keys. Okay, using this public key, we can decrypt the certificate, which was encrypted using the private key, get the public key of the authorized user from that. Okay, so this public key coincides with the public key which the user submitted, and which can verify it is theirs by responding to a challenge. For example, to this way to encrypt something with a private key, which can then be used with the public key to decrypt, and therefore, okay, he is really in possession of the corresponding private key, and it is this person, indeed Mr. Donald Trump, and he is authorized by the authority of someone who signed this certificate to enter the system, then he is allowed to submit transactions to our system. So that's generally how these access certificates are working. Again, these are just signed public keys of authorized users, signed with private keys of the membership service, which is responsible for guaranteeing access to the system. Okay, now a very important thing is that although we normally keep data in a blockchain, for enterprise applications, that might not be enough. Even when we talk about implementing this distributed exchange, or DEX, in the form of smart contracts, you can probably imagine that there are already quite a lot of data. For example, the order submitted and waiting to be matched in the blockchain. Or if we want to keep track of all transactions, I mean not blockchain transactions, but transactions which occurred in our blockchain, in our exchange, distributed exchange as well, and keep them in the blockchain, then the whole history, then it will grow and grow and grow. So there will be more and more and more memory associated with static memory, storage, in terms of Ethereum, if you remember, storage. Associated with our smart contract. It may or may not be okay for DEX. It would typically not be okay for an enterprise data system. Typically, it would use a two-tier design, storing some only critical data and keys and probably hashes of real data in the blockchain. And the real data are stored in external data sources, in traditional data sources, for example, in traditional big databases, data warehouses. Such a combined approach, again, it violates the classical notion of a blockchain. But please bear in mind that enterprise blockchain and classical blockchain are completely different. The classical one was completely public, observable, secured by proof of work. An enterprise one is private, with private membership, with a lot of optimizations in the consensus protocol. For example, if your members are authorized, you no longer need to perform proof of work in order to secure your blockchain. What is the primary reason for proof of work? To prevent your blockchain from being swamped by transactions coming from arbitrary misbehaving nodes, because everyone would be able to set up a node, and then if you want and you hired 1 million Amazon cloud machines, you would set up 1 million nodes, and then you would swamp the network by your own transactions, disorganizing, jeopardizing the operation of the blockchain. In this case, it is not possible. So all members are pre-proofed. Misbehaving members can be disconnected from the network. So there is a notion of an administrator here. Membership access can be withdrawn, obviously. And the only consensus protocol which you really need to run in a private blockchain is not against deliberately malicious nodes or clients, not against a multitude of new clients which for some reason would connect to your network and do unreasonable transactions. That's not possible. It is assumed that the majority of participants are legitimate users. Again, the majority, we can't say that all, but at least it is not possible to create a large number of deliberately misbehaving ones. That's the key difference between the private and public network. Okay? That's not possible. The primary purpose of the consensus protocol in an enterprise blockchain is what? So if we say that, yes, there might be misbehaving nodes, but by design, a very limited, I mean, not by design, by definition, a very limited number of them, we still need a consensus protocol, but for what? In that case. Against just temporal collisions. Because yes, there are distributed nodes, each one is processing, receiving, and processing transactions at different time due to network delays. And it may very well happen that because of the distributed nature, you remember this Byzantine general problem, they can only communicate via messenger. There is no direct access to the state, that they would process different transactions at the same time, resulting in different views of the world. So in order to consolidate the view of the world by all nodes, we still need a consensus protocol. Plus, the consensus protocol would be able to secure the network against a limited number of misbehaving nodes, including maybe deliberately faulty nodes, like those, Byzantine traitors. Okay, if there are n nodes with a Byzantine fault tolerance protocol, how many traitors can we tolerate? Do you remember?
Two.
No, strictly less than 1/3. N is 3 times f plus 1, where you remember where n is the total number of nodes and f is the number of iterators. If there are only 4 nodes, then we can tolerate 1 iterator. If there are 7 nodes, we can tolerate 3 iterators, but the consensus protocol appears to be 2-stage in that case, and it is already quite complicated to draw it on our whiteboard. In general, 3 times f plus 1. That's the Byzantine fault tolerance protocol. I encourage you to review our lectures on Byzantine fault tolerance. So with sufficient number of nodes, it is more fault tolerant than just withstanding 2 iterators. It's better than that. Because the total number n is fixed in this case, or at least it cannot be made arbitrarily large, as well as f is hopefully not made arbitrarily large, then we do not need a proof of anything in this type of network. A simple Byzantine consensus protocol, or let alone, let's say, modern incarnations like hot stuff, which we have discussed, is okay in that case. Proof of work, stake, whatever, is required only for public networks where the number of nodes n is potentially unlimited and anyone is able to add new nodes to the system, and that way jeopardize the security. The point is, for example, in Bitcoin, you are able to add as many nodes as you like to the system, but if these nodes are only inserting transactions but not hashing, so they are not sharing the weight in the proof of work in the network and only swapping the network with transactions, they have absolutely no value in the vaulting for which transactions, which blocks are to be accepted, and therefore they cannot jeopardize the integrity, in this case, consistency of the network. If they do not have, if they do not do any work, they have zero value in the proof of work protocol. And obviously, adding nodes which do proof of work is much more difficult than adding nodes which simply submit transactions. If you really manage to build a sizable majority for yourself, for example, like 51% of nodes in Bitcoin, which do this proof of work, then you have one, and yes, there is a threat, potentially, didn't realize yet, of authoritarian takeover of the network. In Ethereum, there are further steps taken to prevent this, if you remember. So, for example, the hashing problem is deliberately structured in such a way that it is memory intensive, and FPGA type special purpose chips would not be able to tackle it as efficiently. So these are the differences. And yes, this also allows us to refer to traditional data sources, hopefully with some kind of digital signatures with hashes from within the blockchain, and not to store all data in the blockchain. Obviously, in that case, your traditional data sources may become a single point of failure. What if this traditional centralized database fails? That's a big problem. You really need to balance when doing an enterprise blockchain design, to balance your decisions about what kind of hopefully non-critical data you can factor out into these traditional databases without creating a single point of failure. Otherwise, it may undermine the whole idea of a blockchain. So it is a matter of balance, really. Performance versus availability. You typically, when creating an enterprise blockchain, have to interface to other traditional processing platforms apart from traditional data sources. So, for example, in this enterprise system which we are developing in the chain for one of the applications is fueling control of aircraft fueling. We have to interface to two very important enterprise systems of Aeroflot. One of them is their whole enterprise management system, ERP, and which is based on SAP. And another one is a ticket reservation system. Why it is necessary? Because obviously through ticket reservations and flight planning, you would be able to do some kind of advanced fueling planning as well. Again, these traditional processing platforms, they could become single points of failure, which is normal. It would not be normal for a general purpose public blockchain, but that is quite normal for an enterprise one, because if this is to be integrated into our control anyway, and they used to be a single point of failure, then unless they are completely superseded by blockchain, they still remain in place. So they're still single points of failure. There is also a role for the blockchain network operator who provides operational control over the whole thing and so on. So the message is enterprise blockchain systems are quite dissimilar to public Bitcoin or Ethereum or whatever public blockchains. A 2-minute break and we continue. Okay, we are back. So apart from traditional fintech, what are the main applications of enterprise blockchain, and why this enterprise blockchain is a technology nowadays very popular in the Russian Federation? You know that in 2018, by first of all a decree of President Putin and then the order of the government, the Ministry for Digital Development of the Russian Federation identified 9 priority areas of IT development in the country, which are called all through digital technologies or throughout digital technologies. Сквозные цифровые технологии. All through, probably. What does it mean, all through? It means that they're applicable to each and every sector of the national economy, as well as to government and state administration, as well as to national security. So, for example, machine learning, artificial intelligence, robotics, 5G, mobile communications are all parts of this list, 9-item list of also digital technologies. Blockchain is one of them as well. Why it is really important? Because unfortunately, especially in the reality of our Russian economy, any centralized data can be corrupted, in particular corrupted by deliberate action. Not only in Russia, by the way. A few years ago, there was a very funny incident in Italy when drug dealers who imported prohibited narcotic drugs from overseas completely openly operated receiving and distributing drugs arriving in a sea container terminal in one of the ports without just any hiding. Yes, a container arrives, is labeled, receives a barcode, put in storage, then a truck arrives, a container is moved out of storage. It is a legitimate import-export operation. Incredible, you would say. Not at all. They simply bribed the sysadmin who operated the database at this terminal. He obviously inserted extra entries into the database corresponding to those, drug-containing shipments, labeling them as legitimate import, assigning them customs numbers and so on. And here we go. So the whole system of tracking inbound and outbound traffic out of this container terminal appeared to be vulnerable. So there was a single point of failure again to the incorrect operation of the database, which kept track of all shipments and in particular would allow uh, accepting and removing stuff from the warehouse. I wouldn't be surprised if this was all labeled as legitimate import, that they were even paying import tax from those shipments. Why not? Everything was working absolutely legitimately. Until, of course, the street distributors were caught and they pointed to the source of all those shipments. And then the police came to the terminal and everything became clear. And eventually the sysadmin was apprehended. But they operated for a few years. Operated the scheme for a few years. So unfortunately, a corruptible person, is a single point of failure in a large number of transactions. It is even possible, although I would say it is not a common case, but it is possible, and there have been some cases with that, that the distributed ledger, as we learned in the first lecture, it came from the original ledger which kept track of property sales and property ownership rights. Currently, there is a state register, of course, which keeps track, a centralized one as yet, which keeps track of real estate ownership. That's in Russia or in any other country as well. So would it be theoretically possible that someone, for example, bribes an official in this land register service in order to change the record of real estate ownership. With a well-designed system with lots of controls and so on, probably not so easy, but it may happen and probably did happen from time to time. And obviously, if a thing like that happens, then the damage already can potentially be very, very, very substantial. So again, an approach to eliminate this risk is to eliminate a database as a central and centrally administered place where the data are stored, and to have a thoroughly distributed multi-agent database, so that even if one copy is modified illegitimately, then other legitimate copies are retained at other nodes, and therefore this illegitimate state is simply rejected. Or if a transaction which aimed to globally change the state is entered into the system, then at least this transaction is recorded at all nodes, and if it does result in the change of the state, then it is completely transparent what kind of transaction it was, and it can be, for example, if it appears to be fraudulent, then not reversed in the term of in terms of the blockchain. In blockchain, transactions are irreversible, but it can be superseded by another transaction which restores the original state. Not in the sense that the original one is cancelled, but simply it is reversed by another transaction in the opposite direction, something like that, because the whole transaction history is in place. I would say the current trend, and may even be, it is to some extent an overkill, is to try introducing distributed databases everywhere where a centralized database was used previously. We see, for example, healthcare, insurance, manufacturing, supply chain in retail, supply chain in B2B, and so on, relying upon distributed databases. So let's discuss. Okay, for example, for in governance for real estate or any other asset registry, it makes a lot of sense. So you are no longer prone to corruptible officials who could change the asset ownership. Okay, why would we keep, for example, medical records in a distributed environment, in a blockchain? Is there any real value in doing that? What do you think? And yet the healthcare industry, which is here in the center of our slide, is indeed one of very promising and high-profile applications of blockchain technologies. I would ask you, what for? Why would we keep medical
Maybe
blockchain? Yes?
maybe to keep all the records of may you hear me? So to keep all the records about symptoms, all the information about patient, so you will be able to access it from anywhere in a centralized manner, so no one could like affect those data.
Well, generally, yes. I think the reasons are in those situations, including, for example, manufacturing, retail, and so on, are in the following. It is more like, from the point of view of software architecture rather than safety and security. First of all, Yes, imagine that the patient is registered with a number of clinics, okay? He comes to one, he comes to another, and then his medical records need to be unified. So all doctors would be able to see all medical records of that person. How can it be done? Either we can set up a very large central database providing these medical records. That might be okay, but a large central database with all reliability, replication, administration, and so on would be, first of all, costly, and the cost would need to be borne by some central counterparty, which could be the government, for example. In the UK, for a number of years, there was an attempt to build not just for private clinics, but for state-run clinics for the national health system to build a centrally operated database. Otherwise, it was ridiculous. You are registered with one clinic only. If you change it, then your medical records on paper need to be transferred to another one, and it would take up to a month, can you imagine, before they are really, the request is received for transfer, they are shipped, they are received at the new place, they are put into operation at the new place, and within this month, a patient is unable to, well, I wouldn't say completely unable to receive any medical aid, but if he does in the new clinic, then the new doctor has absolutely no access to his medical history and has only access, in the words of the patient himself or herself, which is definitely not nice. And it appeared that building such a centrally managed database for the national health care with, in particular, all reliability, privacy, security, and availability features appeared to be an unmanageable task. The British national healthcare system is a remarkable one in general. It is in a state of totally, how to say, uncontrolled collapse, in the sense that it continues to operate, but it cannot achieve any quality or performance objectives. A few years ago, the state of the system was the following. For 60 million, roughly 60 million population, there were 30,000 doctors in the system, 30,000. Not that many after all. 1 per 2,000 of population. This is a quite low standard. Okay, 200,000 nurses and 250,000 managers in the system, trying to make doctors and nurses working efficiently and each other. And it didn't work. And this central healthcare database miserably failed as well. So about £1 billion was spent on the development of the system. Eventually, it was declared to be too unreliable and too insecure and scrapped. Nice, isn't it? Whereas if we delegate this to a blockchain technology, there are some advantages. By the way, it does not solve the problem of data privacy. Unlike financial transactions, Bitcoin transactions, where the clients are identified by public keys, here there must be some privacy of data. Not all participants in the network are authorized to see all medical data. So we need some kind of access control. But using a distributed ledger system at least solves two other problems. it solved the problem of reliability of the whole system. Imagine that if it is a centralized, large centralized database, and it is down for whatever reason. Either you need a very sophisticated replication and hot and cold copies and switching between them, or and even in that case, you are not completely guaranteed that you would return after it is up again to a consistent state with no transactions lost, or you really risk stopping all healthcare provisions until the system is fixed. And I think some situations like that did happen. In 1990s in the UK, I think something like that did happen with an early attempt to introduce a centrally managed database system for the country, which resulted in a nationwide interruption of healthcare. Not healthcare, it was even more serious. A central management system for ambulance and emergency calls. When you call ambulance in case of medical emergency. When the system was upgraded, in spite of all prior tests performed, it failed immediately upon upgrade. And for a few days, there was a total disruption of ambulance calls and scheduling, which resulted probably in hundreds of people died. So that did happen in the UK. Whereas if your system is fully decentralized, then first of all, even if some copies are not working, some replicas are not working, you can work off other replicas. And secondly, what's even more interesting, the cost of maintaining such a system is silently spread across the participants. If, for example, there is a medical clinic, private or public, or run by a certain doctor, especially in, let's say, in the UK, where it is typically run privately, although the doctors receive refunding from NHS, then the clinic bears the costs of running a local copy. If this is implemented on top of a well-established, verified, and so on blockchain technology, then it may solve the problem. But the problem of data privacy remains in place. So to summarize, the use cases for using blockchain in the industry are typically driven by both technical, economic, and legal regulatory reasons. Uncorruptibility, availability through distribution, and probably even separation of management costs or something like that. I would mention these reasons. How would an enterprise blockchain architecture look like typically? What is important, and this is a philosophy of the distributed ledger systems we are currently considering, in that for an enterprise environment, it is considered to be a little bit too inflexible to have standard fixed solutions in our blockchain. So if it is a consensus, then enterprise systems, like for example the Hyperledger family, they wouldn't just operate with a single consensus protocol. They would make it pluggable consensus. So you can build your solution with whatever consensus you see fit and which is implemented and obeys the API of the whole system. So from that point of view, Hyperledger, well, first of all, Hyperledger is not a software, it is a family of software solutions. We'll see this family very shortly. Secondly, even members of this family are not concrete systems. Rather, they are frameworks, typically frameworks, which allow you to build your own solutions by providing pluggable components. One of them is consensus. Smart contracts, interestingly, in terms of business speak and in particular Hyperledger, they are called chain code. And actually, I would say both terms are equally legitimate, and chain code is a little bit even more to the point, because what? Chain code is the code which is executed by blockchain nodes. So smart contracts and chain code are equivalent terms. Peer-to-peer communications, in particular peer discovery, is called gossip. Again, it is not some particular protocol. It is a term for peer-to-peer communications used at the enterprise level. Why gossip? Because that's how, you remember we discussed briefly peer discovery. That's how peer discovery may happen. You know at least one of the peers, you go to that peer, that's like, gossip spreads. You, or unfortunately, to that extent, how an epidemic spreads. You discover other peers, the gossip is passed to them, and so on and so on. In this case, gossip is peer discovery. It is not that a message is passed through the nodes. Once peers are discovered, then normally you use, obviously, direct peer-to-peer communications. My question to you, by the way, if we talk about peer-to-peer, what are the peer-to-peer communications you have seen? We discussed a little bit, you remember these file sharing applications like ED2K.
You mean real world examples?
Yes, real world. File sharing, we discussed. What others? What are others?
For example, torrent.
Torrents, yes, again, file sharing. My question to you, do you think that, for example, Skype operates as peer-to-peer? So when you make a Skype call, then, well, first it should probably use anyway some kind of addressing service in order to discover the IP address of your counterparty, but then it would use a peer-to-peer communication.
Well, yeah, it does. But it depends on the capabilities of the client, because some clients are unable to establish P2P anyways.
Well, you are right. First of all, I wouldn't say some clients. I would say a vast majority of clients wouldn't be able to establish peer-to-peer communications. That's because these clients are behind firewalls. Typically, when you connect your computer right now, for example, to your local network, it is your local network, 192.168.1x network, for example. These IP addresses have no public meaning. They are reserved for local networks behind your router. And then the router performs the technique known as network address translation, typically port address translation, actually, so that the pair of your local address and the port is translated into an outside address and possibly another port, and in such a way it can handle both outbound and even inbound traffic if this NAT traversal is set up in your router. But in order to be able to accept inbound traffic, you really need to open up the corresponding port address translation in your router. If you don't do it, and typically for Skype you don't do it, then you wouldn't be able to receive incoming calls. Therefore, Skype typically, as well as Zoom, which we are using now, would not be able to operate in a peer-to-peer way from behind firewalls. If you use like ED2K or Kadomle and so on file sharing applications, then um, you need to open up certain ports, which means that, and there is another actually disadvantage of using peer-to-peer. Early versions of Skype, they would use peer-to-peer if they could. So, for example, if they really could establish a direct connection, they would bypass a central server. And you know what? That's a very big problem. In that case, by observing your IP connections currently, and you can do it, for example, in Linux and any other operating system, you can see your currently running applications and network connections established. You would be able to see the direct IP address of your counterparty, which means that your privacy and security could be jeopardized. So, for example, your counterparty talking to you in Skype would be able to see your IP address. And if, for example, your network provider assigns you with a permanent IP address, then your location could be identified, which is not always a good idea, right? For example, you're a journalist or talking to a confidential information source. So Skype currently completely abandoned peer-to-peer communications. And peer-to-peer communications typically require open networks so that TCP connections can be established. In an enterprise environment, you typically can do that by configuring your network in a suitable way. In public open networks, like Bitcoin, in order to be able to receive incoming connections, you obviously need to have a static IP address and to configure your router accordingly. As I said, an enterprise blockchain has data store extended significantly. It is not necessarily ledger data only. It could also be logs and single point of fail external databases, identity services, which we discussed, APIs in order to connect clients, and like consensus layer, cryptography can also be pluggable in enterprise architectures. Here it is, again, just a reiteration of typical entities from which an enterprise system can be built and the meaning of those entities, which we generally know about. You see wallets, for example, for an enterprise system is not for storing funds. It is for storing user security credentials, for example, the certificates used to access the system. That's what needs to be governed for an enterprise system. The system will also generate events which are to be intercepted by other entities connected to the system. So, for example, when a new block is registered in a blockchain, we may use an outside database to store this block as well, maybe for efficiency. We next time will discuss in more detail Hyperledger structural components. In particular, we'll talk about how trust is achieved in this system in a way little bit similar to public networks, and about how the privacy is achieved. For the moment, I just give you an overview of Hyperledger family of software. It is all completely open source under GPL from the Linux Foundation. So indeed, these are frameworks rather than ready to use systems. In your lab, you will see Hyperledger Aroha, which is a mobile framework, whereas a large-scale enterprise one is Hyperledger Fabric. I will be more talking about Fabric, whereas Aroha is, let's say, a lighter scale mobile counterparty. Sawtooth is a very interesting one. I briefly mentioned that in proof of X, if you need proof of X. So if you are in an environment where certification authority and controlled access is not enough and you still need proof of something. There is a new development by Intel backed by Intel hardware design, which is proof of elapsed time. So your chip itself would be able to report the computational time spent for whatever operation. And based on this technology, Intel also, hardware technology, Intel also contributed the Sawtooth open source framework to be used with Hyperledger. Barrow is Ethereum virtual machine implemented within the Hyperledger. So you can run Ethereum on Hyperledger and have full Ethereum compatibility. Explorer is a tool. It is a block explorer similar to what we have for other blockchains, which allow you to view and insert and inspect transactions into the system. Indy is identity management and certificate management, which I already mentioned. Cello is a very important tool because when it comes to deployment of the whole Hyperledger network, you need to deploy it in an enterprise system. So deployment is your enterprise responsibility. It's not like you started just the first node and then you wait for the community to start other nodes and you don't have a control over community. In public networks, yes, it is the case. But in private ones, you need to deploy the whole system at once, at least to start operating, which means typically run a sufficient number of virtual machines, install the necessary operating system, maybe Linux on those virtual machines, provide the security configuration, open up the ports and so on, then put the Hyperledger software, configure this all to work together and start it. So that's what Cello tool is responsible for, because if you have, for example, 1,000 of nodes, then doing it manually or writing scripts by yourself to that end would be, I would say, extremely tedious. Kilt is an interledger bridge to the Ripple distributed ledger system, which we didn't discuss, but it is yet another cryptocurrency. Maybe next term we'll talk a little bit about that, but it is not so important. And Caliper is a performance management tool. So this is the family of Hyperledger tools. Okay, and from well, not from next time, we'll see in more detail how applications are developed at under Hyperledger and how transactions are made. As you can see, Hyperledger Fabric is based heavily based on Kafka, which you know what it is. It is a persistent with deliver guarantees message bus written in Java. Have you been using it in any project? Have you seen Kafka?
Only in lectures on YouTube, but I know that many of us used it.
Okay, therefore many of you did use. I did use it as well for financial transaction purposes. It is nice sometimes. So, for example, you may be sure that the transaction queued would eventually be executed because it is queued persistently and not lost. Although, in my view, it is to some extent heavyweight, and maybe better solutions do exist. We'll discuss this. Actually, to give you one idea, a very, very, very interesting feature of Hyperledger is that execution of smart contracts and updating of state are two different phases of a transaction, which may even be done by different nodes. And that's why there is a service for so-called transaction validation, including executing smart contracts and ordering when they are really put into the sequence of blocks and effectively the state is updated. But more about this is next time. Thank you for today. Any questions, please? If not, then we are done. Thanks. Do you have a lab today? Yes, we do. Very much so. And even on Thursday we will. Thank you. Bye, everyone.